Now we see how to modify the tree search function to make it be a graph search function to avoid those repeated paths. What we do is we start off and initialize a set called the explored set of states that we've already explored. Then, when we consider a new path, we add the new state to the set of already explored states. And then, when we're expanding the path and adding in new states to the end of it, we don't add that in if we've already seen that new state in either the frontier or the explored.
The function graph search takes in one parameter, problem. Inside the function, the first line is to let frontier equal the initial state. A variable called expanded equals the empty set. The second line is loop. The next line is if the frontier is empty, then the function returns fail. The next line is path equals remove choice of frontier. The next line is s equals path.end and add s to expanded. The next line is if s is a goal, then return path. The next line is for an action A in actions. The next line is add action A to the path and add the result state of taking A to the frontier unless the result state of taking action A is in the frontier or in expanded.
Now back to breadth-first search. And let's assume we're using the graph search so that we've eliminated the duplicate paths. Arad is crossed off the list. The path that goes from Arad to Sibiu back to Arad is removed. And we're left with these 1, 2, 3, 4, 5 possible paths. Given these 5 paths, show me which ones are candidates to be expanded next by the breadth-first search algorithm.
The title of this page is Breadth-First Search. It shows the same road network in Romania. Part of this map is the following. The city Arad is connected to Ziran, Sibiu, and Timisoara. Ziran is connected to Oradea and Arad. Oradea is connected to Ziran and Sibiu. Sibiu is connected to Făgăraș, Oradea, and RV. Now, the frontier contains 5 cities, Ziran, Oradea, Făgăraș, RV, and Timisoara. 2 cities, Arad and Sibiu, are already expanded. The question is, which are candidates to expand in the next step?
The answer is that in Sibiu, the action function gives us 4 actions corresponding to traveling along these 4 roads, so we have to add in paths for each of those actions. One of those paths goes here, the other path continues from Arad and goes out here, the third path continues out here, and then the 4th path goes from here, from Arad to Sibiu, and then backtracks back to Arad.
There are 4 possible actions to take from Sibiu: the path to Oradea, the path to Făgăraș, the path to RV, and the path back to Arad. Because Arad is already expanded, we cannot take that action in the graph search.
Now, it may seem silly and redundant to have a path that starts in Arad, goes to Sibiu, and returns to Arad. How can that help us get to our destination in Bucharest? But we can see, if we're dealing with a tree search, why it's natural to have this type of formulation, and why the tree search doesn't even notice that it's backtracked. What the tree search does is superimpose on top of the state space a tree of searches. And the tree looks like this. We start off in state A, and in state A there were 3 actions, so it gave us paths going to Z, S, and T, and from S there were 4 actions, so that gave us paths going to O, F, R, and A, and then the tree would continue on from here. We take one of the next items and remove it and continue on. But notice that we returned to the A state in the state space, but in the tree It's just another item in the tree.
This figure shows a tree structure. The root is the node A. It has 3 children, node Z, node S, and node T. Node S has 4 children, node O, node F, node R, and node A.
Now here's another representation of the search space. And what's happening is as we start to explore the state, we keep track of the frontier, which is the set of states that are at the ends of the path that we haven't explored yet. And behind that frontier is the set of explored states, and ahead of the frontier is the unexplored states.
The root is A. A has 3 children, Z, S, and T. S has 4 children, O, F, R, and A. R has 2 children, L and P. P has 1 child, B. B has 2 children, G and U. L has 1 child, M. M has 1 child, D. Now the frontier contains O, F, R, A, and L. And the explored set contains A, Z, S, and T. The rest are unexplored set.
Now the reason we keep track of the explored states is that when we want to expand and we find a duplicate, so say when we expand from here, if we pointed back to state T, if we hadn't kept track of that, we would have to add in a new state for T down here. But because we've already seen it, and we know that there's actually a regressive step into the already explored state, now because we've kept track of that, we don't need it anymore.
Assume L has another child T. Because T is the parent of L in the tree, we do not explore T from L.